I can see every other page.
All right, guys, page 4 in our packet. We just did example 1, right?
Yeah.
Okay, all right, so let's start example 2.
Yeah, I tried to print it this morning and then my printer was on copy paper and I wasn't gonna go to Staples at like 6 in the morning. So I don't get open until like 9. But well, the ones in the library, the printers in the library didn't work. And then the ones in the art classroom did not work either, so I don't know what's going on with the printer.
I was gonna try this. I was like, I started to print it on the whole business. Getting out. I just thought, I had to grab that Thursday. I didn't even, I was like, yeah.
All right. Example 2.
Page 1.
Page 4. Page 4.
No, I give
All right, guys, let me get your attention, guys. So
No, I got it.
we have, so let me read this problem here. 25-foot ladder. So let's draw it this way. Leaning up against the wall. The bottom of the ladder is getting pulled horizontally away from the wall. So imagine the ladder getting pulled away from the wall, which means it's going to cause this side to come down. So the shape that we are working on is basically involving this right triangle here. Okay. The bottom ladder is being pulled horizontally away from the wall at a constant rate of 3 feet per second. How fast is the top of the ladder moving? And in what direction when the bottom ladder is 15 feet from the wall? So we're working involving the size of a right triangle. So and because of that, I'm going to just go ahead and label each of the sides with a variable here. So I'm going to call this X, Y, and Z. All right, so which equation allows us to connect the 3 sides of a right triangle? Diagonal theorem. So we're going to say X squared plus Y squared equals Z squared. All right, so now that we have our equation, we're going to build our derivative. Every variable gets impacted by time, but first we do power rule. Okay, X squared becomes 2x. All right, we're asking for x's derivative with respect to time, so we need to multiply by what? Dx over dt. Okay. Y squared, same process. 2y dy. Okay, z squared becomes 2z ez over t. Any questions so far? All right, let me talk about what these variables mean. We know what x, y, and z are. Those are just lengths of the side lengths of the triangle. But all these dx over dt, dy, dz, dt, these are rate of changes for these respective side lengths with respect to time. So that means dx dt is concerned about, how fast is this base length changing as time passes. Dy dt is concerned with how fast is this vertical part of the triangle changing. And then dz dt is asking or involving how fast is the hypotenuse of this triangle changing as time passes. So that's what those all these d over dt's mean. Now, if you look, we have 6 variables here. So let's just go ahead and list them out. And then we can go back, reread the problem, and see which pieces we can fill in. And then to the right, if you guys can just save a little bit of space here, we are going to save space for part B. Okay. All right, let's reread the problem here. A 25-foot ladder is leaning up against a vertical wall. What can we assign 25 to be? C, okay. The bottom of the ladder is being pulled horizontally away from the wall at a constant rate of 3 feet per second. Okay. What do you think 3 is going to be referring to? Which variable? Okay, dx over dt. First off, we know it's pulled horizontally away. We know it's going to be x related, but we know it can't be x because we see the word rate, we see being pulled, we see motion problems or words that describes motion. And we know we also see feet per second. So all these context clues indicates that it's not just a static value, it's a moving value. So anytime there's a moving value, it's got to be a rate. So it's going to be dx dt is 3. Now, every time we write down a rate, we have to be the one to decide, is that rate going to be a positive or a negative value? So what do you think this 3 is going to be, positive or negative? Okay, because what's happening to x? Is it getting smaller or getting larger?
Getting bigger.
Getting bigger, yeah. So as the ladder is being pulled away, you can imagine that base length of the triangle increasing. Okay, so the reason that I drew it this way is because sometimes we associate left with negative and right with positive. So I just want to just make sure we understand the direction in this case has no bearing. Okay, so we don't want to look at direction. You want to look at your value as time passes and imagine, okay, is that value getting larger or is that value getting smaller? And that's going to guide whether you want to make your rate positive or negative. Okay, so sometimes down could be positive, up could be negative. So don't look at direction. Look at what's happening to that value. Okay. How fast is the top of the ladder moving? Okay, and in what direction? So what do you think this is referring to? Yeah, you see the word fast. It's got to be a movement, and it's top of the ladder moving, and we know it's going to be involving dy dt. So that's what our goal is. We're trying to find what dy dt is equal to. Now, what do you expect dy dt to be in terms of positive or negative sign? Negative, because getting smaller, right? It's the fact that it's going down, it's not the real reason. It's because we imagine that y value getting smaller as time passes. Okay, so when we solve for it, it should come out negative. Okay. All right. Okay, when the bottom of the ladder is 15 feet from the wall, what's that referring to? X. Yeah, that's 15 feet. There's no time component. It's a static value. So 15 and for x. Okay. Are we good so far? All right. Now, the hope is that we can find 5 out of the 6 values for these variables so that we can just plug in to the equation and find that last missing variable. So let's go back and see if we can figure these out on our own. Well, I have x and z. How can I figure out y? Pythagorean theorem, right? Yeah, if I have 2 sides of a right triangle, I can always numerically solve for that missing third side. So I can say a squared, 15 squared plus y squared equals 25 squared. You can use your calculator. Ends up giving us y squared equals 400. Y is equal to square root of that, which is 20. This is also a variation of the 3, 4, 5 right triangle. So if you recognize that, then it's going to be in proportion to that. But if not, it's okay. You use your calculator, and you should be able to find that y value using Pythagorean theorem. Right. Now, dc dt is describing how fast is the hypotenuse changing. Now, this ladder is 25 feet at the beginning of the problem. How long is it at the end of the problem? Still 25. So what's the rate of change? 0, right? Doesn't change. If something doesn't change, then that rate is going to be Now, not every hypotenuse, not every problem is going to exhibit this behavior. It's just because for the context of this problem, the hypotenuse ends up being constant. And so it's the rate is 0. So for every problem, we have to kind of imagine it in motion and then use that to kind of help guide our the setup of our problem. Okay, so do we have enough information to solve for dy dt? Yes, so we just put everything in, replace your x, your dx dt, your y, your dy dt, your dc dt, sorry, your z and dc dt, and that leaves us with dy dt to plug in and solve. Okay, so we're just going to plug everything in and solve for our missing variable. Okay, any questions so far? All right, I'm just going to enter this in the calculator here. So I reduced the negative 90 over 40, and we're getting the negative number that we were expecting. Okay. And then our units of measure, y is in terms of feet, time is in terms of seconds. So we just put those two units over each other. Good. So 0 is talking about the rate of change of this hypotenuse. So the ladder is 25 feet at the beginning.
Yeah.
Okay. How long is it at the end of the problem?
Oh, yeah. Oh, stay
Same. Okay. So if there's no change, then the rate is 0. Yeah. Okay. Any questions with part A? Okay. Part B. At what rate is the question?
So direction.
Oh, sorry. Yeah. So we're just going to say moving down. Yeah. Thanks. New path.
No, I will do it first.
All right, part B. At what rate is the area changing? So what shape do we have here? Triangle. Okay. So we have to build our area formula first before we can do anything with derivatives. So what's the area formula for a triangle? 1/2. Okay, so let me write that down. 1/2 base times height. Okay. This is, let's just go ahead and reuse the variables because we're going to reuse all this data here. So what represents the base? X, and height is y. Okay, so I'm going to have 1/2 x times y. Okay, so that's our starting equation. It says, at what rate is the area changing? What variable are we ultimately looking for? It's not showing up yet, but we're looking for, yeah, dA over dt, which is the derivative away, right? So we're going to turn a into dA dt. So that's the derivative. Now the right side, can we just say 1/2 dx dt times dy dt, or is there something else we have to involve here? Product rule. Okay, we have to go through the product rule on the right side. Now, if it was 1/2 x plus y, then we could make it dx dt plus dy dt separately, but these are connected and they're multiplied. We have to go through a product rule. So this is my f, this is my g. Sorry. And we have to build our derivative one piece by piece. So f prime g f g prime. Okay, 1/2 x. What's 1/2 x's derivative? 1/2.
1/2.
But what happens with x? Everything is impacted by time, so x becomes dx over dt. Right. Before it would become 1, but now the related rates is going to impact every variable, since now time is the independent variable, is no longer x. Okay, g doesn't change. F doesn't change. Now what's g prime? What does y turn into? dy over dt. Yeah. Any questions about how we built the derivative using product rule? All right, everything, this is the same moment in time, 15 feet from the wall. So all the data that we gathered from part A is relevant. So we can just plug all that in and then use our calculator to get a numeric answer. Okay, try that. And then just before we enter all that in, let me just talk about units real quick. Area over time. So what do you think our units will be at the end? Areas in terms of what? Square feet, and then time is second. Yeah, so square feet per second. That will be our final unit. Okay, so if you're ever struggling with units, look at your variable and then just identify the units of the variable and just put them over each other. Let me zoom in so you guys can see this work. If you represent your answer as a decimal, that's fine. Just the standard for AP exam is 3 decimal places. Yeah.
If you find d of y over d of t, you have to find area. That's what.
I'm sorry.
That's what you're finding.
Yeah, we're trying to find the rate of change of area. We're trying to find what that DAT is equal to.
Can we do it with all 3?
Only
with all 3. With d of u x over d of t.
Yeah.
Okay.
But I'm not sure.
No, I
question. Okay.
Yeah.
So we don't involve dZdt because the area doesn't require the hypotenuse. So we only need dxdt, dydt, x and y to help us build our variable that we're looking for. Give you guys a moment to finish. And again, we're just reusing all the values that we found from part A. All right, page 5. Does anybody still need to look at this page? All right, here we go. A spherical balloon is being inflated at a rate of 10 cubic centimeters per second. Find the rate of change of the surface area of the balloon at the moment when surface area is 64 pi. Now, this is talking about the volume of a sphere and surface area of a sphere. These formulas will be provided for you. Anything that is more than just a circle, rectangle, a triangle will be provided for you. Same thing on AP exam. So any geometric 3-dimensional formulas. You don't have to memorize them. Those will be provided for you. Okay, so those are given. Volume is 4/3 pi r cubed. Surface area is 4 pi r squared. Now, anytime we're dealing with related rates, we're always going to be finding the derivative. So let's just get the derivatives out of the way, and that way we just focus on just plugging values in, and we're just trying to find the missing variable. Okay, so the only variable that's involved here is v and r. So we just have to find these two derivatives. 4/3 pi is just a coefficient. It's just going to hang out in front. It's not going to change. Okay, so one piece at a time here. Let's do v. V becomes dv over dt. 4/3 pi will stay. It's just a number attached to the variable. The derivative that we're looking for is that r cubed. What's r cubed's derivative? Power rule. What's r cubed? 3r squared. But we're asking for r's derivative with respect to time, so we also need to multiply by what? Yep, dr over dt. Okay. Are you okay so far? Right. Some students were asking from previous class, they were saying, hey, that's a 4/3 pi is a constant. How come that doesn't go to a 0? Good, is multiplied by r. So I know this is not the formula here, but if some reason it was 4/3 pi plus r cubed, then yes, then you can force that to be a 0 because that's by itself. But if it's multiplying with a variable, it stays, right? Like if I have y is equal to 8x squared, the derivative is y prime is 16x. We don't get rid of the 8, it just hangs out in front. So if it's being multiplied, it stays, but if it's by itself, then it does go to a 0. All right, let me do some cleanup here so that we have an easier equation to plug in. I see a 3 above in the denominator and numerator, so I'm just going to go ahead and just cancel these out, just to make my dv/dt a little cleaner to work with. So 4 pi r squared dr dt. Okay. Okay, let's do the same thing with s. Let's just get the derivative out of the way and see if it can help us. All right, s becomes derivative, just ds over dt. Yeah. 4 pi r squared. What does this become? Good. Yeah. Or you can just bring that 2 down, make it 8 pi in one step if you want. But yeah, 2r. All right, let me do a little bit of cleanup. Okay, we're done with the calculus. Now we're just going to read the problem, try to figure out what information they have for us, and then we're just going to plug in and hopefully find the variable that we're looking for. All right, so here are the 4 equations available to us. We may not use all of them, but these are what's available to us. So depending on the problem and what's needed, we will use them accordingly. And these are just the unclean. This is just these are just simplified versions of the ones above. Okay. Okay, let's go back to the problem here. A spherical balloon is being inflated at a rate of 10 cubic centimeters per second. All right, what variable do you think that is talking about? Okay, let's break this down here. Cubic centimeters. Cubic centimeters, that's what? That's 3-dimensional, right? So that's volume, right, per second. So it's dv over dt, right? dv. So even if this is not enough to kind of help you decide what's going on, the units should help you a lot, right? Cubic centimeters, it can't be surface area. If it were, it'll be centimeter squared, or square centimeters, but cubic, it's got to be volume. So it's got to be dV over dt. So at the bottom here, I'm just going to list out what information that I do have. So I'll say dV over dt equals 10. Do I want to make that a positive or a negative 10? Positive because
It's growing.
growing. Yeah. So if a value is growing, you want that rate to be positive. Okay. Sorry, centimeters, cubic centimeters. Find the rate of change of the surface area of the balloon. What are we looking for? Find the rate of change of the surface area of the balloon. Good. It can't just be S because you see the word rate of change. So we must be talking about ds dt. And that is what our goal is. We're trying to find the rate of change of the surface area with respect to time. Okay. At the moment, when the surface area is 64 pi. What's that value for? S. Yeah. So S is 64 pi. Okay. We've done all the information gathering, and now it's just, can we use all these tools to help us get to our answer? Okay. Are we good so far? Okay. Let's start at the end and what we're trying to achieve. We're trying to find ds dt, right? So let's just look at what ds dt is asking for, because if we have the values for ds dt, we can just plug in and solve. So we're looking for ds dt. And ds dt needs the radius and dr dt. Remember, pi is just a number, so we already have that. Do we have radius and dr dt given to us? No, right? We have s and dv dt. So we don't have the data explicitly given to us, but maybe these can help us get to where we need, right? So our ultimate goal is if we can get to r and dr dt, then we're in the clear. We can just plug those in and get our answer. So the question is, can this S help us get to one of the values that we need? How can that 64 pi help us out? Okay. Good. So if I put that 64 pi in for S, then I can solve for R. If I can solve for R, then I have one piece of the puzzle that I need, right? So this can help us lead to the radius. Okay. So we'll do that in a second. I just want to kind of help us see the big picture a little bit. So that's going to be something we're going to do, that we're going to need. Now, once we find R, we're still needing dr dt. So we still don't have dr dt. So the other question is, well, what we do have is we have dv dt. So how can, if we look further down the problem, how can this dv dt value help us out to get to where we want to go? Do we have a dv dt equation? Yeah, so that 10, we can put that 10 in for this dv dt. And assuming that we already found R, then we should be able to get to dr dt. And then that should get us to where we want to be. All right, so S is going to help us eventually get to R. And then dv dt is eventually going to help us get to dr dt. And then once we have these two values, then we can plug in and solve. All right, so let's work on the S portion first. So I'm going to put 64 pi in for S.
I got it's rounded 7.09.
For what?
S.
For S. So, okay, let me talk about this here. We want to hold on. We want to hold on to that pi just so that we would like to represent our answer in exact values. So if you're, unless I think like 36 Pro can handle, like if you plug in pi, it'll still return you pi. But I think on the TI-8384, it may give you a decimal number. So leave pi out of the calculator and then just treat it like a variable and just kind of put it where it belongs. So let me just do this here. I'm just going to replace 64 pi in for S. And I'm just working on this equation to see if I can get an intermediate variable that I need. So I'm going to divide both sides by 4 pi. Divide these two, I get 16.
4.
Good. Take the square roots. Now, technically, I have plus or minus 4, but why do we not worry about -4?
Because still increase.
Okay, and also we're talking about the what? Radius, right? So for our problem, right, radius doesn't make sense as a negative value, so we're going to just keep the positive value. So R is 4. All right, so that's one piece that we need. The other piece that we need is dRdt, and let's go to our dV/dt equation because we have some information from that side of things. So I'll replace 10 in for dV/dt, and here I already have R, so I can also replace R with 4, and that should allow us to move towards solving for that dRdt. I'm going to multiply this out. So 16 times 4 is 64. We're going to bleed into example 4. We're not going to do example 4. So if you need additional space, I'm going to need it. So I'm going to use the space down here to finish my problem. I'm going to reduce here just so that it's easier numbers to plug in. So 10 and 64, I can reduce to be 5 and 32. Okay, so we're almost there. We have the last two pieces that we needed to find to solve for ds/dt. We needed the radius, we found that. We needed the dr/dt, we found that. So now we can put into our ds/dt equation and find that value. So 8 pi r gets replaced with 4. dr/dt gets replaced with 5 over 32 pi. All right, 8 times 4 is what? 32 times pi is 32 pi. I have 32 pi in the numerator. I have 32 pi in the denominator. What can I do? Cancel them out. And I'm just left with 5. Okay, let's talk about units for a moment. ds over dt is 5. Surface area. Focus on that word area there. What's the unit for area? Yeah, centimeters squared per second. Good. Time is seconds. So there's our value here. Yeah.
Oh, I was looking somewhere else.
Let me talk about something that I've seen some students have trouble with, and that's just it's not a big thing, but just to point out, sometimes when we divide by pi, we think of that pi as notation, and sometimes we think, oh, pi doesn't matter where it belongs or where it is. So I see some students they just let that pi always be in the numerator, but it's not just a notation; it's a value. So if you put that pi in the denominator versus putting it in the numerator, it's not the same thing. You're dividing by pi versus multiplying by pi. It's different. So I think sometimes we associate pi with just something that sits in front of the fraction. But if algebraically, if pi ends up in the denominator, it needs to stay in the denominator. We can't just let it you can't just make it 5 pi over 32 because then you're changing the value of your answer of that rate. So just be aware that if pi is supposed to be in the denominator, you have to leave it in the denominator. it's not the same thing as just moving it up to the top. Okay, any questions? All right, cone problems. This is going to be the most algebraically challenging of this unit. So just know that this is going to take some time to get used to, but first time through, let's just follow the steps. Don't feel like you have to be able to master this whole process on the first time go around. But I'm going to go slow, ask questions, but as long as you can follow from step to step, that's all we need to worry about. We still have multiple days. Every day we'll do one. I think, after a couple of times, it'll become more familiar. Okay, but for now, if you can just follow the steps, that's good enough. Okay. All right, so we have a cone tank, vertex down, 10 feet across, 12 feet deep. So I'm going to just go ahead and label. If water is flowing into the tank at a rate of 10 cubic feet per minute, find the rate of change of the depth of water when the water is 8 feet deep. So there's water inside this cone tank. And I want us to see something here, that there is a cone within a cone. There's a cone that is obviously the shape of the tank, but then the water inside the tank is also getting shaped by the tank. So do you see how the water inside the tank is also its own cone as well? It's a smaller cone. So we have a cone inside a cone, and we're going to use that to help us build the relationship that we need. Okay. So here's the volume formula that we provided for you. Volume is pi over 3 r squared h. Now, with these types of problems, we don't want to go ahead and find the derivative, because if we do, we have to go through product rule. And if we went through product rule, a bunch of variables will show up we're going to have too many variables and not enough data. So the idea is that there is a relationship between radius and height because of similar triangles. And we're going to find one in terms of the other and try to get the volume equation down to a single variable, either radius or height, depending on what the problem is asking for us to do. Okay. So we're going to do this here. We're going to create a similar triangle just with this portion of our problem. Okay, so I'm going to create just a right triangle just for that part that I highlighted. So we have a triangle within a triangle, but these triangles are proportional to each other. So we have the dimension of the tank. The radius is 5 because they tell us the diameter is 10. And then the height is 12 because that's provided for us. Now, the cone formed by the water, is it a constant value? Okay, water's flowing in, so these both are variables. Okay, these are both changing. So we're going to call one R and the other H. Okay. So we're going to build a relationship between radius and height of the water level, because these are continually changing, but they're going to be changing in a predictable way in relation to each other. So we're going to say this. We're going to say the radius of the small cone is to the radius of the large cone as the height of the small cone is to the height of the large cone. And for every cone problem, you're just going to set it up this way. All right, let's get the fraction out of the way. Let me cross multiply here. So I'm going to say 12R is equal to 5H. Now, we don't know whether to solve for R or H yet, because we don't know yet which variable that we're going to work on. So we're going to go back and reread the problem, gather more data, and then we'll come back and decide, okay, which variable do I want to solve for and which variable do I want to replace? Okay. All right, let's go back to reading the problem here. A cone tank, we already have the dimensions here. water is flowing into the tank at a rate of 10 cubic feet per minute. I know we don't see this variable yet, but can you tell by the units what this is referring to? 10 cubic feet per minute. What? Good. Cubic feet, that's volume. Per minute, it's time, so dV over dt. So let's go ahead and just write that. I know we don't see that variable yet, but eventually it will show up. Positive or negative 10? Positive. Because adding water, so volume is growing. So positive 10 cubic feet per minute. Okay, find the rate of change of the depth of water. Depth of water, what's depth of water referring to? Which variable? Rate of change of that. So therefore, good, dH over dt. Okay, so rate of change of depth of water is talking about dH dt. So that is what we're looking for. When the water is 8 feet deep, what variable is that? H. Okay. Okay. This is the big hint here. The hint is, okay, we're looking for dH dt. dH dt is related to H. So if we can get our equation in terms of H, just H alone, then the derivative will just naturally produce dH dt on its own. Okay. So because we're looking for dH dt and dH dt is related to H, we would like our volume equation in terms of H, which means we want to get rid of what? R. So we want to find a replacement for R. If I want to find a replacement for R, I'm going to solve for R so I can find something to replace R with. Okay, so I'm going to solve for R. So I would like to replace this variable. So I'm going to solve for R. So R is equal to divide by 12. So 5H over 12. So this is my key to help me get my volume equation down to the variable that I want, so that when I do the derivative, it will produce the variable that I want to show up. Okay. All right. Let me write the equation again, and then we can make the substitution. I over 3 R squared H. I'm just going to make a replacement. Replace R with 5H over 12. Eventually, this will become a much easier problem to find the derivative, but we don't want to find the derivative now. If we did, it will be a product and chain, a whole mess. We can avoid all that just by cleaning things up and combining the variables and getting the coefficients in front. So right now, we're going to do a bunch of cleanup. We're going to get rid of the parentheses. We're going to square everything inside the parentheses and then try to merge some of these numbers together. So 5 gets squared, H gets squared, 12 gets squared. Okay, so I want us to see that we can merge all the coefficients together. The 25 pi, the 3 and 144 can all be put together under one fraction. So 25 pi, and then 3 times 144, if you plug in the calculator, it gets you 432. So that's just one messy coefficient, but it's just some number in front of my variable. And then H squared and H, what is that? How many H's do I have? H cubed, right? So it's just H cubed. So now from here, the derivative should be a lot cleaner because V becomes dV dt. We're just doing power rule for H. And then the coefficient, as messy as it is, it's just going to hang out in front. It's not going to change. Okay. All right, let's build the derivative here. So V becomes dV dt. Coefficient is not going anywhere, right? It's just a number in front of my variable, so it's just going to stay. Okay, the only derivative is really just H cubed here. What's H cube's derivative? 3h squared, okay? But we're asking for h's derivative, so we need what? Times dh over dt. Okay, that's the hardest part. The hardest part is getting to this volume equation, getting it cleaned up, getting to the derivative, and now everything is just plugging in and solving for our missing variable. Okay. Let me just do a little bit of cleanup here. You don't have to. I just figured that I can just put some pieces together before I plug information in, but it's not a big deal if you don't. So if we look here, dv/dt, we have that value ready for us to use. So that's 10, that's good. H, we have that value ready for us as well. H is 8. And then dh/dt, we have that variable waiting for us to solve, right? So everything we need, we have values for, or the value of the variable we're looking for. All right, so now we're just plugging information in. So replace dv/dt with 10. Replace h with 8. I'm just going to work on cleaning up. So I'm going to plug in the calculator. Don't leave pi out of the calculator. Just have it kind of sit there in the numerator. So 75 times 64 all over 432. So 75 times 64 all over 432. Make the calculator convert it to a fraction if possible. And it gets us down to 100 pi over 9. Again, I'm leaving pi out of the calculator. Otherwise, it'll just give me a whole decimal value that I don't want to hold on. That will prevent me from getting to present an exact value. So I'm just plugging that in, making the calculator reduce and getting that fraction for me. And now I can just move this over, right? So dividing by 100 pi over 9 is the same thing as what? Multiplying by what? The reciprocal, right? So $90 over 100 reduces to be 9/10. Careful, pi is still in the denominator, so it needs to stay in the denominator even at the end of our problem here. Sorry, this is equals here, equals. So 90 over 100 is just 9/10. Pi stays in the denominator. Height and time, let's do our units here. So height is in terms of feet. Time is in terms of minutes. So feet per minute. Okay. A couple of things that I want to point out that just to highlight some of the issues that students have with this problem or a problem like this. Here's a big issue. The big issue is when they give you that height, the tendency is students want to start entering that in because they're like, well, I have h is 8. Why not just start putting in 8 in for all the h's? Do not use until after the derivative. This is the height of the water level at that moment in time. Is the height of the water level always going to be 8 feet? It's not. So if you insert that 8 into the proportion, that means you're stating that the height is always staying at 8, which is not true. So you want to hold on to the h variable until the derivative is set, and then you can involve that 8 in for h. But if you put that 8 in for h, you lose the h variable. If you lose the h variable, you're not going to be able to find the derivative, and dh/dt is not going to show up for you.
Saying if you plug in 8.
Yeah, if you plug in the 8 too soon, you're going to lose the h. If you lose the h, the dh/dt is not going to show up, right? So Okay, good. So, no homework this weekend, but Monday, we're going to, do another one of these and we're just gonna practice our way through, okay?
Like,
Baby,
four fails. This kind of makes sense.
Yeah. Not that one, stack of cone, no, hell no. No, that's the cone.
Oh, yeah, what happened?
David did not miss a good day. David did not miss a good day.
30 seconds left.
You know what, the hardest one was that. That's the hardest one. That was the hardest one out of all.
No, they saw it.
And mine.
Kind of do sense.
Yeah, I know, I'm gonna get out there. Fucking 7 times.
So, you're saying radius of a small cone. I just follow every line. And I just. No. So I moved this over to the other side. That's a fraction.
Like for real. There finally wasn't. I'd be like, so that, yeah, we'll be doing this my last, so we can like edit it, and we'll probably have to edit it all again, but I understand make probably wrong.
Hey, bro, I'm still ready. It's rad. Are they over two?
Oh, yeah. There's what I want to see. There's what I
You know. It's just up here.
I want to do that. Yeah, I don't even know what it is. Someone who wants to use what? Yeah. No, it doesn't take that long. No, I brought her up the top of my, so in my bed, she said hours yesterday. It's lunch on everything, but once you know how I'm doing, you got it. Like, I know. Yeah. So no, why was you that? I was.